Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Today, we're going to be talking about why the internet is so cool. Which, I'm a big fan, but obviously, I just think it's really cool. And there's a whole bunch of stuff that we're going to learn about today about what makes it so cool. So, over the course of today's video, we're going to be talking a little bit about why the internet is cool, just kind of like motivating that idea. Then I have a definition. It's kind of my own definition, but it's very similar to the one on Wikipedia. It's certainly relatively well accepted, that we'll use kind of as a roadmap for learning about all the cool things that make the internet as awesome as it is. I talked a little bit in class last week about how the internet as presented in the book is very, dry. It's looking at a few very specific details about the internet, but it really doesn't drive home what's so awesome about it. And so these lectures aren't really going to cover the stuff that's in the book, but they are going to talk about what I think is important about what made the internet as popular as it is today, why it's so important, and why it's so successful as a way to do stuff on the internet, because it's just like, it's by default. That's a thing that we have now that we didn't have 20, 30 years ago. That whole concept of a worldwide, instantaneous, data-based global communication network just didn't even exist in the popular mind. With all that said, let's get started. There are three super awesome things that I want to focus on that come to mind when I think about what's so important, what's so cool about the internet. And one of them is that it's incredibly flexible. It allows you to use different network layer technologies to send messages from one place to another directly. So I can use 802.11 Wi-Fi to get from my laptop to the router, the Comcast router in my home. And then that will work just the same as plugging in a cable, or just the same as some other technology if somebody came up with it. I can switch out that link layer technology as well as switching out the application layer technologies. I don't have to get anybody's permission to deploy a Chris TCP or a Chris HTTP. I just say, well, I'm going to do that on one end. Somebody else is going to do that on the other end, wherever they are in the entire world. And we're going to rely on that capability to build these new and exciting and interesting things on top of what already exists. So beyond that, probably the most amazing of all of these ideas is how it doesn't all fall apart immediately all the time, because everybody wants to send their messages as fast as they possibly can. Right? If I want to send something and I'm allowed to send at a certain level, why don't I just send at that certain level? In reality, if everybody did that, then nobody would be able to get any of their messages through. And this is a somewhat subtle point, and we're going to cover some of the reasons why this is the case. But the super amazing part here is that the internet doesn't completely fall apart because everyone decides, even though I could try to send faster, I'm going to slow myself down voluntarily so that everybody can get their messages processed successfully by the network. And finally, we have this thing called the end-to-end argument in network design that's tied to the flexibility that I talked about earlier. But in addition to just having that cool flexibility, the end-to-end argument really gives us a technically better network than we would have had otherwise. And it also allows for a lot of the scaling that we see in the internet as a network of computers that we didn't see in the previous worldwide telecommunications mechanism, the telephone network. These were two very different networks that were designed in two very different ways. And to hit on some of these points that I think are really important in CS361, where we care a lot about how engineers approach a problem and ask a set of questions like, I could design this and it would function correctly if I did it this way or this way or this way. What am I trying to optimize for? And how am I going to make a decision based on what I think is going to be the best way to architect a specific system? This end-to-end argument not only gives us the flexibility from that first point, but it also gives us the scalability that has made the internet stay successful, even though there are billions more users on it than there were when it was originally designed. So with that out of the way, I'm going to dive into my definition of the internet. What is the internet? I'm going to read this right from the screen so I get it exactly correct. The internet is a network of networks that delivers messages using a best effort packet switch delivery mechanism. What the heck does that mean? Well, that's what we're talking about here today. First, a network of networks. The idea here is that when I have my host on one side and you have your host on one side, and say we wanted to send a message back and forth. Maybe we're using the Signal encrypted messaging app and I want to send a message directly to you. What I would do is I don't I don't find a way to directly send that message to you, but instead, what I'm going to do is I'm going to decide, okay, I'm going to find you, I'm going to find your IP address or however it is I'm planning on sending this message all the way to you. And then I'm going to create a message that I send directly to my home router because I am part of a local area network with a router in it. And so I can directly send my message to that router with instructions that also say, hey, this has to eventually get to my friend over on the other side of the internet. And the router's job is to exist on 2 different networks at once. And so one of these is my home, and one of these is, say, Comcast. And a router is just like any other host on the internet. But what's special about it is that it exists in 2 different networks at the same time. It exists on my local home network as that default router that I send all of my messages to if I have to go someplace else. And it exists as one of many different routers that's connected to a cable modem that's connected to a central router at Comcast that is going to forward that message on. My router decides who am I supposed to send this message to get it closer to its destination, and it sends it. And that router is going to be connected to another router in another network. And that router is going to be connected to another router, et cetera, et cetera. And then eventually it's going to get to another network where you are, and it's going to send that message. So we're going hop by hop by hop by hop to get from one point to another. And we say there's 2 different responsibilities that we have when it comes to sending a message from one place to another. One is just getting it from one host to another host. But the magic here is saying, in addition to that, we're going to have another decision being made. That is, which host do I send it to get it closer to its ultimate destination? So that's why we have this collection of networks that is connected by routers that forms the internet. The next important part of this definition is best effort. This is another one of those really amazing kind of mind-blowing things that I really think is awesome about the internet. So the important thing here is that when we have these different machines, all these routers that are performing the routing on the internet, the only thing that they need to do is try to send messages as fast as they possibly can. They have no hard guarantee of they have to deliver a certain number. They have to signal back to the originator that a message got dropped, et cetera, et cetera. And they don't have to say, hold on to a message and keep trying to send it until it successfully gets sent to the next hop. Every single router is told, when you receive a message, try to send it as fast as you possibly can. But if you run out of space to say, hold on to a message while you're sending things out of a slower link, you can just drop it on the floor. And nobody's going to say, hey, you didn't follow the internet protocol because you dropped that message. So to draw this a little bit visually, the idea here is that if we draw those routers from that last slide here, each of these routers has inside of it a buffer that is going to fill up with messages that need to be sent out the other side. The router needs to look at the message, find its destination address, and figure out which router to send it to next. Because while in a simple situation like our home router example, it's only connecting 2 networks. If something's coming from one network, it's obvious that it's going to the other network. A router can easily be connected, for instance, to 3 different networks, and it has to decide which of these links is the best way for me to send it to get it to its ultimate destination. And all of these different links that are all connected to this individual router are probably going to have different speeds, and they're certainly going to have different numbers of packets coming in at any given moment in time. So for instance, if I can send at a gigabit per second coming in here, and I'm going to send as fast as I possibly can, when that particular router decides that, oh, the messages that I'm trying to send are all going through to some ultimate destination D over here on the other side of the slide, it's going to decide, oh, they all have to go through this link right here. But what if this link right here is only 100 megabits per second? What will happen is if I send a short burst of messages, like I'm sending one picture that couldn't possibly go through as fast through that 100 megabit link as it goes through this 1 gigabit link, what that router is going to do is it's going to send things out as fast as it possibly can out the other side. But everything that it can't send because it doesn't have enough speed to do so, it's going to put into a buffer until that buffer fills up. And one important thing about internet traffic is that it's bursty. Sometimes we're going to send a whole bunch of bytes as fast as we possibly can, but then a lot of the time we're going to spend not sending anything. Think about, for instance, reading a web page. You click on a link on Reddit and you see a picture, and you, at a human, like, it takes you a few seconds to read it, realize the joke, laugh at it, and then click next or whatever have you. So over the course of the first, say, 100 milliseconds of that time, you're sending and receiving bytes. But for the next 4.9 seconds, nothing really is happening. The network isn't doing much. So we can leverage this bursty idea combined with this idea of putting buffers in the middle of the network to absorb these bursty loads. And so even though I used my 1000 megabit link to send that request or send that message, only a little bit of it comes out the other end per every unit time, and everything else gets put into that buffer. So best effort comes into play here when I have filled this buffer up. When someone has filled that buffer up and another message comes in, you just say, you know what, drop that message, don't even try to deliver it. If the host that was trying to send that message really wants to get it through, they will try to send it again. And when they try to send it again, hopefully this buffer will have drained and I'll be able to send it successfully through this other bottleneck link. But the most important thing to remember here is that these types of message drops are just normal. They're expected in the network. They're completely legal. They don't cause any sort of really bad situation. They are part of the entire system that was designed from the get-go to expect this type of failure to happen. Another really important part about the internet is that it's a packet switched network. This is in contrast to what's called a circuit switch network. This is in contrast to what's called a circuit switch network, where I can create a connection from point A to point B, and every single message is going to immediately flow all the way through that circuit along a specific path. You can imagine a circuit switch network is like an old-timey telephone network where the telephone operator connects one part of a cable to one plug, another part of a cable to another plug, and makes that call go through. That creates a circuit, in that case specifically an electrical circuit, from the source to the destination so that those messages can flow. In contrast to that, the internet is packet switched, where instead of deciding how to set the connection up and then allowing the messages to go back and forth and back and forth and back and forth, the internet says every single time I receive a message anywhere, I'm going to make a decision about how to forward it. So if we redraw that example from the previous slide, what will happen here is even if I'm sending hundreds and hundreds of different messages from myself to my destination, every single one of those routers is going to make a decision based on the destination address in that message about who to forward it to at the next hop. This seems a little bit more expensive than setting up a circuit like we would in a telephone type network, but it actually ends up being one of the most important, powerful parts of the internet's design. This gives us the resiliency of being able to switch where we send a message so that it can route around failures. So for instance, if this router had a connection here, that goes to a different router, that goes to a different router, that goes to the destination, what can happen is that if something bad happens to this router right here, then we don't have to recreate an entire circuit to allow us to use this alternate path. If this router here knows that it can either reach its destination by this first router or the one below it, it's just that the one below it is more expensive because it takes more hops. It can make that decision as soon as it realizes that the top router has failed. It can immediately start sending those messages along a different path. And I don't have to make any changes to my code or my decisions. The destination doesn't have to make any changes to how it's receiving messages or who it's receiving those messages from. Those individual routers in the middle can just decide, hey, based on who I know I can talk to at this moment in time, what's the best way for me to send this message? This adds a lot of resilience and a lot of extra simplicity in the middle of the network that pays off in the overall design. So these three really cool properties of the internet, that it's a network of networks, that it delivers best effort service, and the fact that it's packet switched and uses the end-to-end principle that we're going to see a little bit later, all of these combine to make the internet as amazing and awesome and super, super cool as it is. Over the next few lectures, I'll be covering each of these points in turn to dig a little bit deeper into what makes them special and what makes them important. Thanks so much, and I'll see you in the next one.